Hello, everybody. Welcome back. This is 6B, the normal distribution examples. Okay, there's something I realized I might not have mentioned during our graphing lesson. It's peakiness. So, the normal distribution, right? Unimodal, symmetric, and mound-shaped, right? Some distributions, though, go like this. They're very peaky or pointy at the top, okay? There's a more, statistical word for that, but we can just call it peakiness. And when you try to apply the assumptions of the normal distribution to something that's really peaky, you can run into trouble. Okay? So if your distribution looks like that, if it's really pointy at the top, it's not mound-shaped, and you're working on your dissertation project and you're wondering what's going wrong, then, email me. We'll talk about it. Okay. So peakiness is another property of distributions. Okay, so getting into some examples related to this thing called z-scores. Slide 2. Okay, so height is something that's assumed to be normally distributed in the population, right? So most people are kind of in some average, and some people are very, very tall, and some people are very, very short. For women in the U.S., the mu, or the population mean, is 65 inches, and the sigma, or the population standard deviation, is about 3.5 inches. So find the z-score of a woman who is 67 inches tall. Guess who happens to be 67 inches tall? Yep, that's me. Well, if you round up to, that last inch. Okay, so slide 3. What we do is we subtract x, that's my height, 67 inches, from mu, the population height, and we divide by the sigma, the population standard deviation. And so 67 minus 65 is, 2, divided by 3.5 is 0.57. Let me double check that. Let me double check my math on my phone here. 67 minus 65 divided by 3.5. Yes, 0.571, blah, 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 blah. So rounds to 0.57 standard deviations. Because we divided by the standard deviation, we are now in standard deviation units. Okay, so my score is 0.57, or anyone who's 67 inches tall, is 0.57 standard deviations above the mean. Yay, I'm taller than normal. Okay, for whatever that's worth. Let's see. So you see how we got that? About half a standard deviation above the mean. Okay, now, but the standard deviation is only 3.5. 3.5 inches. So I'm not that much taller than the mean. Okay, tables of z. So now we can use tables, and now there are apps and online calculators. But back in the day, there were only tables to find the area under the distribution. So to find various areas and therefore percentiles under this standard normal distribution. Okay, it can always help to draw. So like, I borrowed my daughter's Crayolas, whatever you have on hand to draw. It always helps to draw the distribution, to actually visualize it. Okay, so here's an excerpt from a z-table on slide 5. So if you go from, and you see it has 4 columns. A z column, distance from the mean to whatever that Z is, and then what is the larger portion and what is the smaller portion. So if you look at the first row, and mean, it could be like whatever your X is to Z. So we have a normal curve, right? If your Z-score is 0, remember that's right in the center for the standard normal distribution. And the larger when you calculate a Z-score and your Z-score comes out to be 0 as an equal to the population mean, then that means that 50%, the larger proportion is 0.50 or 50%, right? This proportion is 50% on this side, and this proportion is 50%. Okay? Sorry, my handwriting is terrible there. Okay. So on either side of this line. And remember when we were doing the M&Ms, I put a pencil there. So yeah. Okay. So now that's the table, but it makes more sense when we try an example. So what does the distribution look like if the Z-score is 0.03 standard deviations? So a person with a height of 0.03, and that's positive, 0.03 standard deviations above the mean height, okay? So that would be, draw our normal distribution, drop our center, 0, the mean Z-score, and we're saying that for a person whose Z-score is 0.03 standard deviations, right? So like 1 standard deviation is usually around there. Okay, that's 1 SD. Okay. So 0.03 is really close to 0, right? So we're talking, it's not that different, right? And so we know that it's 50% of the population would fall below 0, and we're just 0.03 over, right? So am I doing that right? 3%, 0.5 point. Yeah. Okay. We're 0.03, 0.30, 0.5, 0.3. Okay. So I would guess that's 0.03. I would guess it would be 50.03 on this side and 49.97% of folks on that side. Here, let me see. What does the next slide tell us? Not helpful. Okay. Let's go into another example. I'm going to have to check that out. Z equals 0.03. What was my Z-score again? For my height, 0.57. Yeah. Okay, I'm right. This is what happens when you use someone else's slides. Okay. Now let's go to the next one. Slide 7. This is a standardization example, and we're going to use the example of a Dear Abby reader. And so she writes, Dear Abby, you wrote in your column that a woman is pregnant for 266 days. Who said so? I carried my baby for 10 months and 5 days. My husband traveled to China for work, and it could not have been conceived any other time because I only saw him once for an hour, which would have been enough time, and I didn't see him again until the baby was born. I don't drink, I don't run around, and there is no way this baby isn't his. So please print a retraction about the 266-day carrying time because I am in a lot of trouble. That's from a San Diego reader. Okay, let's look at this somewhat silly example. Next slide, slide 8. So documented data, okay? Gestation time follows a normal distribution with a mu of 266 days, a mean of 266 days, and a sigma of 16 days, or a standard deviation of 16. So X is our gestation time. And the question is, what percent of babies have a gestation time greater than 310 days, or 10 months and 5 days? Okay, so where does this reader of Dear Abby fall on the normal distribution, right? So this is our standard normal, mean of 0, standard deviation of 1. Okay, so we need to convert these days from this reader to a standard z-score. We do this reader's number of days pregnant, 310, minus the mean, which is 266, divide by 16, and we get 2.75. So let's say this is 1 standard deviation. This is 2 standard deviation. This is 3 standard deviations. So there's 1 sigma, 2 sigmas, 3 sigmas. That's where they would fall. Okay? Let me see that. There. Okay, so 2.75 puts this reader right around there. Okay? So 2.75 standard deviations from the mean. Okay? Now, we want to know what percent of pregnancies happen, way over here. Okay? Or we could find out happen over here and subtract. But we'll look above this line where our Dear Abby, or to the right of this line where our Dear Abby reader had their child. Okay, slide 9. So the z-score was 2.75. Right? So I slide down to where the z-score is 2.75. From the mean to that z-score, okay, this distance, from the mean to that z-score, the table tells us is 0.497. Okay? That's the proportion. The proportion of people who would fall between the mean and 2.75. Okay, now the larger portion, so all of this, okay, all of this, all of the people, where's another color? Here's a good one. All of the people, the larger portion, all of these people who are under the curve below 2.75 standard deviation units. And that is 99.7. 0.997 is the proportion, or 99.7% of people, right? Now, how about above? We're trying to figure out the area over here, above 2.75, the area under the curve over here. And according to our table, that last row, the smaller proportion is 0.003. So over there, if we're going from 2.75 out to infinity, there's 0.003 is the proportion, or 0.3% of pregnancies, just a very small number of pregnancies, will last longer than 310 days. Okay, as long as 310 days or longer. Okay, next slide. Wait, before I go on to the next slide. So, is it possible that a person could be pregnant for 310 days? There is a slight possibility, but it's only 0.3%. Okay? So you'll have to decide if the husband who has presumably returned from China should believe that this baby is actually his. Of course, they could just, get a genetic test and not have to worry about the statistics here, but that's me getting too much into the example. All right, reverse standardization. Sometimes we need to convert a standard normal Z into a non-standard normal X. Okay, so if we want to start with how many standard deviations away is someone, and then go work backwards to figure out, well, what is the real number? Like the real number in the previous example, the unit was in days, but we converted it to standard deviation units. But it's also possible to go backwards. So, for example, what is the length of pregnancy below which we have 5% of the population? Okay, so let's draw a picture of that. There's our normal curve, mean of 0, and we want to know, okay, if we have 5%, let's say I'm shading in 5%. Okay, if that's 5% that I've shaded in there, what's the length of pregnancy there? Okay, so the X. Okay, so we're going the opposite way, and I'll go back to the table. And I'm looking at slide 9, and I'm looking for the row that has the smaller proportion. The smaller portion is 0.05, so that's 5%. That looks like that's the 1, 2, 3, 4, 5, 6th row. The smaller proportion is 0.05. The larger proportion, of course, since it's 1, the area under the curve is 1. The larger proportion is 95, right? All of this is 95% of people. So the small proportion is 0.05. That's like third from the bottom. And larger proportion is 0.95. The mean to Z is 0.45. That means the Z score is 1.645. And we're going below 0, so I'm going to say negative 1.645. Okay, let me go back to slide 10. So, X, we're trying to figure out the number of days, okay? X equals sigma times Z plus mu. And we're trying to figure out the number of days. X equals to, what was the sigma on these pregnancies? It was 16. 16 times our Z, well, negative 1.6. Negative 1.645 plus mu. And mu was what? 266. Plus 266. Okay. See how I'm doing that? Let me go back. Okay. So now I just do the math. 16, clear, 16 times 1.645 equals negative 26 plus negative 26.32 plus 266 equals 239.68 is what I get. And some of you are very sharp, and so if I make a mistake, I know you will catch it. So about, which is about, I'm going to do my squiggly equal sign to say about 240 days. So if a woman is pregnant for 240 days, we know that only 5% of pregnancies are that short. So, yeah, if anybody's at the 240-day mark and they're like ready for it to end, the chances are not likely that it'll end that soon, because only 5% of pregnancies are that short. Okay, so that's how you kind of go backwards to go from the, like, a percentage to a z-score to the actual unit that you're interested in, which in this case was days. Okay, here's an NCAA example. So the Division I SAT requirements are that athletes are required to score at least 820 on a combined math and verbal SAT. In the year 2000, SAT scores were normally distributed with a mean of 1,019 and a standard deviation, or sigma, of 209. So what percentage of students, have scores that are greater than 820? Is this requirement, really stringent and would make it difficult for talented young people, athletically talented young people to perform in the NCAA, or is it more reasonable? Let's find out. Okay, slide 12. So our z-score, again, we take whatever our x is minus mu. So 820 is the requirement. I'm on slide 12. We subtract the mu, the population mean, of 1,019. We divide it by 209, which should equal negative 0.95. Okay, on a z-table, you're not going to find negative numbers. You can just look for 0.95, all right? So we find 0.95 on the table, okay? So that's about one standard deviation, right? We'll remember those. If you keep saying the units, it makes it a little bit easier. Okay, so 0.95 standard deviations. So what percentage of SAT takers in 2000 scored above the NCAA cutoff? Now remember, this was negative. So here's where a picture comes in really in handy. So I draw my normal distribution. There's my mean of 0. 1, 2, 1, 2. Okay. Minus 1, minus 2. Plus 1 standard deviation, plus 2 standard deviations. Okay. So, and we're saying the z-score is minus 0.95. So really close to minus 1. All right. Really close to minus 1, right? So that would be minus 0.95. Okay. And what percentage of takers scored at or above that cutoff? Okay, so we want to know above. So we want to know all of these people. Okay, which is the larger portion, right? In this case, we want to know the larger portion. And it looks like the larger portion is 0.8289, or like 0.83. Okay, so 83% of SAT takers score at or be above this NCAA this NCAA cutoff, which means it's not so stringent that we're going to be keeping talented athletes from being able to do something that they really enjoy. Okay, sounds like the baby is calling me, so I'm going to hit stop here, and I'll talk to you later.